Control B6. Make a slide in. Hi, hello. So let's just start the presentation for today. Wait a minute. Good evening all of you. Myself Subham, PMRF, Department of Chemistry, IIT Guwahati. So I'll be the TA for this course, Thermodynamics, Classical to Statistical, which is taught by Professor Sandeep Paul, Department of Chemistry, IIT Guwahati. So we will start with concept of heat and work, first law of thermodynamics, internal energy, enthalpy, introduction to entropy. These topics are discussed in week 1 in the tutorial. So we will first look into summary of this, and then we will go into solving the questions and doubts. So sir has taught this already. I'll just quickly remind it. So the system and the surrounding. The total universe is sum of system and surrounding, and the system and surrounding are separated by a boundary, and the system is it is a region or matter which is under study, so and separated by a boundary. Then we have studied this heat, work, and heat is nothing, just energy transferred between system and surrounding due to difference in temperature between them, and work is energy transferred between system and surrounding due to imbalance forces. And the sign convention, heat is positive when heat is transferred to the system, and it is negative when heat is evolved by the system. Similarly, when work is done on the system, it is positive, and when work is done by the system, it is negative. So it is a sign convention. Formulas for pressure, volume, work. Sir already gave the expression in the NPTEL video, so I'll just revise you these formulas only. So work done is minus of P external del V, where del V is the change in the volume, and P external is external pressure applied to the system. And isothermal reversible expansion work for ideal gas will be work is equals to minus nRT final volume divided by initial volume. For adiabatic reversible expansion, work for ideal gas will be nR T2 minus T1 divided by gamma minus 1. Gamma is Cp divided by C. Free expansion. When a gas is allowed to expand into vacuum, it is a free expansion. So when gas is expanding from free expansion, then there is no heat evolved, there is no work done, and no change in internal energy, and there is no temperature change. That will help in some questions as well. First law of thermodynamics. First law of thermodynamics states that energy can neither be created nor be destroyed. It can only be converted from one form to other. And its mathematical expression is the change in internal energy is the sum of heat and work done. So what is internal energy? It is the total sum of all the energies that are associated with the system due to its molecular arrangement and its motion. So all type of energy are considered here, like electronic, vibronic, and all this rotational and other energies as well, thermal energies, kinetic, all kinetic and potential energy are into it. So this is internal energy. Enthalpy. Enthalpy is the sum of internal energy and P del V. So del V here is delta NGRT. Delta Ng is change in number of moles of gases in the reaction. So heat enthalpy is positive. When enthalpy is positive, it is said to be endothermic reaction, and when it is negative, it is said to be exothermic reaction. Heat capacity. So other important this is other important thermodynamic quantity. The heat capacity, it is amount of heat required to raise the temperature by 1 degree. So heat capacity at constant pressure, Cp is nothing but Qp, heat at constant pressure divided by delta T, that is dH by dt at constant P. Similarly, at constant pressure, it is volume, sorry for the typo mistake. Heat capacity at constant volume, Cv is equals to Qv divided by delta T, that is du by dt at constant volume. For ideal gas, Cp minus Cv is NR, and mostly Cp is greater than Cv. That you can also see from the formula delta H is equal to delta U plus P delta V. So if we consider it as Qp, heat at constant pressure, and it as heat at constant volume, so there is something adding into heat at constant volume. So heat at constant pressure is greater than this heat at constant volume. Similarly here, Cp is greater than Cv. Then sir taught us this Kirchhoff law also. The change in internal energy at temperature T2 is equals to change in internal energy at temperature T1 plus integration over Cp. Cp is a function of temperature here. Cpt dt from temperature T1 to T2. After that, limitation of first law of thermodynamics. The main disadvantage of first law of thermodynamics is that it does not involve disorder or randomness of the system. So to quantify this disorder, we need a state function, and that state function is known as entropy. So entropy is introduced to study this disorder and randomness. So second law of thermodynamics, for a spontaneous process, entropy of a universe always increases. It is second law of thermodynamics. Entropy always, change in entropy is always greater than 0. So if there is a temperature change, or if there is a spontaneous process occurring, then entropy must always be greater than 0, and at equilibrium it is equal to 0, since there is no change in temperature. So let's start the question part. It was just a simple revision for us, so that we can connect to our questions now, and we are solving only week 1 questions here, in which we studied work, heat, and this first law of thermodynamics, entropy, introduction to entropy, and then specific heat, and etc. So this is the first question. Among work, heat, internal energy, and entropy, which are W and U are path function, but Q and S are state function. Option, these are the options. W and S are path function, but Q and U are state function. S and U are path function and Q and W are state function. W and Q are path function, but U and S are state function. So correct option is W and Q both are the path function, but internal energy and entropy, U and S, they are state function. That's our taught us in class also. So here W and Q are path function, but U and S are state function. Option D is correct for this question. Then next question, the exact differential df of a state function f x y among the following is x dy, dx minus x by y dy, y dx minus x dy, 1 by y dx minus x by y square dy. So how we calculate this exact differential? So for that I have solved it in the page and pasted here. So for that we first since f is a function of x and y, so we write so I'll take a this, give me a second only. I'll open a board here to solve this. Give me a minute only. Okay, it is here only, I guess. So we can solve it in a whiteboard. So function of x comma y can be written as curl f divided by curl x into dx plus so I'll explain it there only. It is not working very fine, so without wasting time I'll directly move to the solution there. I have done it by pen only, paper and pen. So here, since f is a function of x and y, it can be written as df by dx at constant y into dx plus df by dy at constant x dy. It is a simple differentiation of the function f, and if we consider df by dx at m and df by dy as n, and by derivating m with respect to y and n with respect to x and equating them, if both of them are coming same, then it is a state function, and otherwise it is not a state function. Or you may call it as exact differential as well if it is equal. So in the first option, x dy, so there is not any dx part, so we can say that m is 0 and n is x. So m is 0, n is x. So when we differentiate m with respect to y at constant x, it will come 0, and when we differentiate n with respect to x, that is n is equal to x, so this will come 1 only. So left hand side is not equal to right hand side, so it is not a state function. Then second option, dx minus x by y dy. So m is 1, so when we differentiate 1, it will give only 0, and then n is x by y, so when we differentiate it, it will give some amount, so some value it will give, so that will not be equal to 0, So this is also not a state function. Then this third option, y dx minus x dy. So m is y, n is minus x. So differentiate y with respect m with respect to y, we get 1, and n with respect to x, we get minus 1. So this is also not a state function. Then we move to part D, 1 by y dx minus x by y square dy. So when we differentiate 1 by y with respect to y, we will get minus 1 by y square. And when we differentiate x by y square with respect to dx, we minus 1 x by y square with respect to dx, we again get this minus 1 by y square. So it is solved here also, minus 1 by y square and minus 1 by y square. So left hand side is equals to right hand side, and hence it is a state function. The correct answer is, the correct option is D. So now we move to the next question. For the reaction, this is the simple reaction. Wait a minute. Let me check if anyone is in waiting room or not, and then I'll start again. No one is in waiting room, so we will start it again. So this is the question. This type of questions are there in assignment 1 also. So solving this question can help solving assignment 1 also, and also some questions are conceptually, they can help you in competitive exam as well. So for the reaction X2O2 to XO2, this is a liquid and this is a gas. At 298 Kelvin, give the value delta U is equals to 9 kilojoule and delta S is equals to 84 joule per Kelvin. Delta G is equals to what? These are the 4 options. So delta G is equal to delta H minus T delta S. So delta S is given, temperature is given, all we need to calculate is delta H only. So delta H, as I have shown before, let me move to that slide, as I have not any whiteboard is not working, so I will show it there only. So here it is, delta H is equals to delta U plus P delta V. So delta V can be written as delta NGRT. Delta NG is change in number of mole of gas. We are not considering number of moles of liquid or solid here, because they are not as random as the gases. So we skip their number of moles, like for the sake of this randomness. That I will explain in this entropy question as well. So delta H is equal to delta G, delta G is equal to delta H minus T delta S, and delta H is equals to delta U plus delta NG RT. So by this formula we can calculate this. Delta NG, change in number of mole of gas, is 2 minus 0, that is 2. So delta NG is 2, and other quantities are given. Delta U is given and delta S is given. So first we need to see that these units, this is in delta U is in kilojoule and delta S is in kilojoule, joule per Kelvin. So we need to convert this kilojoule into joule, or this joule into kilojoule. So our answer is in kilojoule, so we will convert it into joule. Then we after the getting the answer, we will again convert into the kilojoule. So as 1 kilojoule is equal to 10 to the power 3 joule, and delta G is equal to delta H minus T delta S. Delta H is equal to delta U plus delta NG RT. Delta NG is sum of mole of gases product minus sum of mole of the gases reactant. Then delta U is given, delta S is given, temperature is given, The solution is delta H is equal to delta U plus delta NG RT. So delta NG is equal to 2. By putting all these values, we will get an answer. So delta U is equal to, in the joule, it is 9000 joule plus delta NG 2, and that R gas constant, it is 8.314 joule per Kelvin per mole, and this temperature is 298 Kelvin. So by solving this, we are getting delta H is equal to 13.95 kilojoule, and delta G is equal to delta H minus T delta H. Delta H is given, it is 84 joule per Kelvin. So by converting into kilojoule and adding these quantity, we are getting minus 11.08 kilojoule. Minus 11.08 kilojoule. This is option A. A given mass of gas, next question, a given mass of gas at 0 degree Celsius is compressed reversibly and adiabatically. So this is the main thing, reversible and adiabatic, to pressure 20 times. This is the pressure. The initial value, what is the final temperature of the gas? Here we need to calculate final temperature, and the process is adiabatic, reversible adiabatic process. So an initial temperature is given, initial pressure is given, the adiabatic pressure 20 times the initial value, so it is 20 times Pi. So as we know, the famous this equation we know is P V to the power gamma is equals to constant. By solving that equation, we can get these values as well. T to the power gamma into P to the power 1 minus gamma is equals to constant. So since gamma is given as 1.42, so we need to solve this only. So while it is constant, so we can equate initial and final conditions. So T1 to the power gamma, P1 to the power 1 minus gamma is equal to T to the power gamma, P to the power 1 minus gamma. So now keeping temperature at one side and pressure at one side and solving the equation, we can get the answer. So T1 by T2 to the power gamma, P2 by P1 to the power 1 minus gamma is our equation 1. Now put values in equation 1. So values are given here. Temperature 0 degree Celsius, so we convert it in Kelvin, 273 Kelvin. T2 we need to find out, so T1 is 273, gamma is 1.42. Pressure 1 is, if let's say it is P1, then pressure 2 will be 20 P1 as it is given. Pressure 20 times the initial value, so P1 is P1, then P1, if P1 is P, then P2 will be 20P. So this P1 will cancel out this P1, and 1 minus gamma is 1 minus 1.42. So by solving this and taking logarithm on both sides, we can solve and get temperature. The answer is A. Now we will move to the next question. For the combustion of 1 mole of liquid benzene at 25 degrees Celsius, the heat of the reaction at constant pressure is given by. This is the reaction, delta H is given. So what will be the heat of the reaction at constant volume? So heat at constant pressure is nothing, it is delta H, and heat at constant volume, it is nothing but delta U. So we can calculate it by the equation delta H is equal to delta U plus delta Ng RT. So delta Ng is 6 minus 15 by 2. We can neglect this liquid one. So delta Ng is, we only need to calculate delta Ng. So 6 minus 15 by 2. So solution is here. Delta H is equal to delta U plus delta Ng RT. Delta Ng is equal to 6 minus 13 by 2, that is 7.5, that is equal to minus 1.5. So by putting these values, and delta U is given, delta U we need to calculate, and delta H is given. So delta H is given, and delta Ng we calculated, and then R, the answer is in kilocalorie, sorry. So R, value of gas constant R, is equal to 2 calorie per Kelvin per mole. So we put this value 2 here, and the temperature is given 25 degrees Celsius by converting it into this Kelvin, 298 Kelvin. So solving this, we get the value in calories, and dividing it by 1000, we get the kilocalorie, and the answer matches with A. The next question: what will be the work done could be obtained from an isothermal reversible expansion? Isothermal reversible expansion of 1 mole of Cl2 from 1 decimeter cube to 50 decimeter cube at 273 Kelvin using ideal gas behavior. So given is that volume changes from 50 decimeter cube to 1 to 50. This is in liter only. Decimeter cube is liter only. So this is from 1 liter to 50 liter at 273 Kelvin, and number of mole is given 1, and the reaction is isothermal reversible expansion. So we know the formula for this, that is equal to W is equals to minus nRT ln V2 by V1. So V2 is given, V1 is given, number of mole is given, temperature is given. So we can simply calculate this. W is equal to minus nRT, n is 1, so RT ln V2 by V1. So by solving this, R is, since the answer is in kilojoule per mole, so we are using 8.314 joule per Kelvin per mole, and then we will convert it to joule into kilojoule in the last step. Temperature is given to 73, so this is 2.203. You convert ln into log. By solving this, we can get the answer, and then answer is matching with A, minus 8.8 kilojoule per mole. Consider the following PV diagram for an ideal gas. Follow the diagonal path from A to B. So this is a path is given from, they are saying that it is going from A to B, and other step path also given, A to C and then B, A to D and then B, but they are giving that A to B. From A to B, temperature is constant, so it is an isothermal process. Then at A, volume is 10 liter, and at B, volume is 0.5 liter, and pressure also changing from A to B. Pressure is 1 atm at A and 20 atm at B. So the question is work done on the gas in the process from A to B. What is the work done on the gas? So work done, this is an isothermal reversible process. So expansion A to B. No, sorry, it is not an expansion. It is from A to B. It is compression. So we saw in initial slide that work done, when work is done on the system, then it is a positive quantity. So answer is, all the answer is in positive. So work compression, work when compression is done, work done when compression is there, it is positive only. So we can solve it by W is equal to minus nRT ln V2 by V1 only, but V2 is 0.5 and V1 is 10. From A to B it is going, so 10 is our V1 and 0.5 is our V2. So by solving this, we can get the answer. So it is solved here. It is solved here. So minus nRT ln V2 by V1 it is, so V2 is 0.5 and then V1 is 10. So we can solve it nRT. So this nRT, from the gas equation PV is equal to nRT, we can solve it, and since it is an isothermal process, so P1 V1 is equal to P2 V2 as well, as we know that P1 V1 by T1 is equal to P2 V2 by T2 in common, but if T1 is equal to T2, then P1 V1 is equal to P2 V2. So that equation we can use here, and RT is equals to P1. We are doing this because we do not they do not give any value of n, number of moles. So we do not know n, so we have to convert this nRT into some known quantity. So that is why I am converting it into PV term. Since we know P and V only, so I am converting this nRT into PV. Since VV is equal to nRT and P1 V1 is equal to P2 V2, we can see here also P1 V1. So P1 is 1 and V1 is 10. So it is P1 V1 is equal to 10, and then P2 V2, it is 20 into 0.5, that is again 10. So P1 V1 is equal to P2 V2. So here I will simply written PV is equal to nRT, and that is equal to 10. Simply written this. So we can say that nRT is equal to 10 and ln 20. ln 20 by coming by 0.5 by 10. So it is 50. Sorry, 5 by 100. So we can take the inverse of it and remove this positive, negative charge. This will be 10 by 0.5 to the power minus 1, and then minus 1 power from log can come in front, and then minus into minus can be plus. So nRT ln 10 by 5, ln 100 by 5, sorry. So this is nRT ln 20. So answer is 10 ln 20. I hope this is fine, that I said here that nRT is equals to PV, because we do not know n, we cannot solve this nRT. We know R, we know T, but we do not know n. So to convert this n into other known quantity, I convert it into PV. And since PV is constant for thermal isothermal process, we can use it either P1 V1 or P2 V2. They both will give and same answer, that is 10 ln 20. The next question in the same graph is saying that for the above process, delta H is equal to W, work done, delta H is equal to heat, delta H is equal to delta G, that is gives free energy, delta H is equal to delta E, that delta E is same as delta EU. So this is internal energy only, this is enthalpy, this is gives free energy, this is enthalpy, this is heat, this is enthalpy, this is enthalpy, and this is again work. So this is an isothermal process, and we can calculate the, for isothermal process Q is for isothermal process delta U and delta H both are 0, that is delta E and delta H here, these both are 0, so they will be equal only. So since we know that these both internal energy and enthalpy both are function of temperature, so they will be 0 at constant temperature. That is why option D is correct here. So for isothermal process, delta T is equal to 0, delta H is equal to delta E. Correct answer is D. So I'll have water, some water. Sorry. Give me a minute. Just for water. टीवी में निकल रहा है यार, खत्म हो गया फिर कमाई तेज का गाना सारी सेंटर डोंट शो करो वो घंटे जीवन में sorry, let's do it again. So where were we? I hope this question is everyone will understand this question. So now we will move up to the next question. The criteria for the spontaneity of a process is delta, this is S is entropy, S system greater than 0, delta S of surrounding greater than 0, delta S of system plus delta S of surrounding greater than 0, delta S of system minus delta S of surrounding greater than 0. So we know that from the second law of thermodynamics, entropy always increases, entropy of the universe always increases, and the system and surrounding both are the part of universe. So the correct option among this is this delta S system plus delta S surrounding greater than 0, because this is the entropy, this total is the entropy of the universe. So this option C is correct, since it is entropy of universe is greater than 0. Change in entropy of universe is greater than 0. This is also the second law of thermodynamics. So very simple question. The enthalpy of fusion of ice at 273 Kelvin is 6 kilojoule per mole. Enthalpy of fusion. And enthalpy of vaporization of water at 273 Kelvin is 44.83 kilojoule per mole. The enthalpy of sublimation of the ice at 273 Kelvin is, so let me again try with this whiteboard. This is very simple question again. So it is not working, so I'll explain it here only. Enthalpy of fusion of ice. So it is the conversion of ice to this water, liquid water, and then to the vapors. So enthalpy of fusion of ice. So from ice to this liquid water, it is converting by 6.01 kilojoule per mole, and then enthalpy of vaporization of water to the at 273 Kelvin is 44.83 kilojoule per mole, and we need to calculate the enthalpy of sublimation. So as we know that enthalpy is a state function, it does not depend on the path. So we can if we are going from solid to gas, we can always go through two steps, from solid to liquid and liquid to gas, and they both will, from going from solid to liquid and liquid to gas and going directly from solid to gas, both will give same amount of enthalpy. So sum of enthalpy of fusion and enthalpy of vaporization will give us the enthalpy of sublimation. So here in the question, enthalpy of fusion is given 6.01 kilojoule per mole, and enthalpy of vaporization is given 44.83 kilojoule per mole. So we can add these quantities and we can get the answer. It is very simple question. So it is matching with A, option A, 50. It is a positive quantity, and we know that converting ice from ice to vapor, it is an endothermic process. So delta H is positive only. The next question is, 1 mole of monoatomic ideal gas is transformed from 300 Kelvin and 2 atm to 600 Kelvin and 4 atm. The entropy change for this process is, so for this I think sir will discuss this formula in next class, or maybe it is discussed already. So I'll explain this. So you need to sir will solve this question in class, so I'll just tell you the how to solve this. So delta S is NCP ln T2 by T1 plus NR ln P1 by P2. So this is the formula for change in entropy. So what is given here? Temperature T1, pressure P1, temperature T2 and pressure P2. And what all we need? Temperature T2, T1, T2 and pressure P1, P2 and Cp. And for Cp we are given that it is a monatomic gas. For monatomic gas it is 5 by 2 R. So we know all the quantity and we can put it in our formula and we can get the answer. So Cp is 5 by 2 R, N is 1, so 5 by 2 R ln T2 by T1, T2 is 600 and T1 is 300, so it is 2, 5 by 2 R ln 2 plus N is again 1 R ln P1 by P2, P1 is 2 and P2 is 4, so 2 by 4, that is 1 by 2. You can write it as minus R ln 2 as well. So 5 by 2 R ln 2 minus R ln 2, they will give 5 by 2 R minus R ln 2. So this is 3 by 2 R ln 2, that is 1.5 R ln 2. The correct answer is 1.5 R ln 2. This is option A. Next question. 1 mole of an ideal gas undergo a cyclic process A, B, C, D, A. A, B, C, D and A. Starting from point A through 4 reversible steps as shown in figure. The total work done in the process. So we need to calculate the total work done, and it is going from A to B and then B to C and C to D and D to A. And we know work done is not a state function, it is a path function. So we have to calculate at each path. So from A to B, volume changing from V1 to V2, and it is a isothermal process. From A to B it is an isothermal process since temperature is constant to T1. So we can calculate it by the formula minus nRT ln V2 by V1. So the formula will be minus nRT ln V2 by V1. Then from B to C, the volume change is 0. So ln V2 by V1 is only ln 1, so ln 1 is 0. So here work done is 0. From B to C, the change in volume is 0, so it is the work done is 0. From C to D, again it is a compression. A to B it was the expansion, and from C to D it is an compression. From C to D, volume is reducing from V2 to V1. So the formula is again the same that we use from A to B, minus nRT ln V2 by V1. So now V2 is V1 and then V1 is V2. For this process, initial volume is V2 and final volume is V1. So we will add these. This is all layer. Let me read it out for you. Total work done in cyclic process from A to A, B, C, D, A is for work done from A to B, work done from B to C, work done from C to D, and then D to A. And since we know that WAB and WCD are isothermal reversible processes, so we can apply the formula minus nRT ln V2 by V1, V final by V initial. So for the first process A to B, it is V final is V2 and V initial is V1, and for C, from going C to D, V final is V1 and V initial is V2. By putting these values and adding all the parameters, and again it is at temperature T1, so it is at temperature T2, so formula minus nRT ln so for this it will be minus nRT ln V2 by V1, minus nRT 1 T1, temperature is T1, minus nRT 1 ln V2 by V1. For this it is minus nRT 2 ln V1 by V2, as final velocity is V1. So again from D to A, work done is again 0 because there is no volume change. So by adding these two, we are getting R T2 minus T1 ln V2 by V1. So correct option is D, R T2 minus T1 ln V2 by V1. I'll solve some more questions, but if you have any doubt, you can clarify it now. In these questions I have solved. If you have any doubt, you can clarify. I'll start again. Please ask if you have any doubt. Don't have, and then I'll continue. So okay. Okay, where? Actually, your voice is not coming properly, so can you please say it again, or can you please write in box. Okay, what is the doubt? Which question? Question. So yeah, it is there in the assignment, no? So let me open that assignment and I'll clarify that. I'll try. Actually, we are not solving the assignment here, so this is for helping you to solve that assignment. What is the doubt here? The state of 1 mole of an ideal monatomic gas is changed reversibly from 1 liter 10 bar to 10 liter 1 bar. 1 liter 10 bar to 10 liter 1 bar. So it is going from this state to this state by path 2. Two paths are given, path 1 and path 2. So what is the question? Work done by the gas and the change of internal energy are more for path 1 than path 2. So let's see. So internal energy, we know it is like exact. It is not a path function, it is exact. So state function, sorry. So internal energy going from 1 or going from 2, it will be same for both the processes, internal energy. And then work done for process 1. So upper part of process 1, there is a change in volume, but for lower part there is not any change in the volume. So this one work done is 0, where there is no volume change, there is work done 0. For this and this process there will be some work done. So let's calculate it. Oh, I'm sorry, I'll present it now. Are you able to see now? So let me solve this. Yeah, so have you understood what I was saying, or do I need to repeat it? Work done by the gas for path 2 is less, work done by the path 1 is more. Oh, work done by gas for path 2 is less, work done by the path 1 is more. It is same only. And then internal energy for both the path are same, internal energy for gas in both the path is same. So they are basically saying the same thing only, no? Okay, I'll look into this question and I'll get back to you. I think if you can mail me, I will give you my mail ID and I will give you the solution. Let's see. I'll see the options again. I haven't solved this assignment, so I will give you the solution. Okay. Just mail me. Okay. So I am writing my mail ID here. Okay. Sorry. Why it is happening? Laptop is not working. So this is like you can add at @gmail.com. So I have written my address. Okay. You got it? So we'll again start the solving the questions that we were solving. What? Actually, we are not supposed to solve that assignment because student will solve those questions, and if you have any doubt you can ask in this discussion forum. We are here to give you the way how to solve these questions, like not exactly the questions. That is why I have put some similar type of questions here. Okay, you can ask in discussion forum and I'll reply there. Okay, question 3 only, no? Okay. Which of the following statement is not true for an ideal gas? For an ideal gas, enthalpy, entropy, both are at constant temperature, both are 0. So apart from that, there is only one option, C. It is not correct. So okay. Enthalpy and entropy at constant temperature. Option A, option B and option D. These all are 0. So they are all true and option C is not true. Okay. So let's start the questions again. That we have solved. This question we have solved already, no? adiabatic reversible expansion of an ideal gas, the plot of log T versus log V is linear with a slope equal to. So we know this equation as TV to the power gamma minus 1 is equal to constant. This is derived from PV to the power gamma is equal to constant. So by taking logarithm of this, log T is plus log T plus gamma minus 1 log V is equal to log of constant. So log T is equals to log C plus 1 minus gamma, that is the slope, log V, that is this is equation of a straight line, y is equal to mx plus c. So log T at x axis and this log V at x axis, and then this will be the slope minus 1 minus gamma, and then this will be the intercept. So slope is 1 minus gamma. Slope is 1 minus gamma. So option C is correct. If we get similar question like PV to the power gamma is equals to constant, then we can solve that also. Log P plus gamma log V is equal to log constant. Then we can separate this. Log P is equal to log minus gamma log V plus log constant. So then for P versus V, log P versus log V curve, minus gamma will be the slope. Okay. So the next question, 2 liter of an ideal gas at a pressure of 10 atm expand isothermally at 25 degrees Celsius into a vacuum until its total volume is 10 liter. Find heat and work. So the key here is the vacuum. So vacuum, since vacuum is here, so this external pressure is 0. This is a free expansion only. So key for this question is this vacuum only. Other things are just like for the illusion. So this vacuum, this is a free expansion. So for free expansion, work done is 0. And since P external is 0, so work done is 0. So then this heat for an isothermal reaction, delta U is 0. So then delta U is equal to Q plus W. So delta U is 0, then W is equal to minus Q. So then heat is also 0. So the correct answer is B is equal to B, Q is equal to minus W is equal to 0 liter per atm. It is solved here. For vacuum, P external is 0. This is a free expansion. So work done is 0. If work done is 0 and delta U is 0 for isothermal reaction, then Q is equal to minus W is equal to 0. So answer is the next question. Predict in which of the following entropy increases. So we are looking for increase in entropy. A liquid crystallizes into a solid. From liquid to solid, randomness decrease. From going liquid to solid, randomness decreases. So here entropy will be less than 0. It is not increasing. It is change in entropy is less than 0. So it is not increasing. It is decreasing for option 1. Temperature of a crystalline solid is raised from 0 Kelvin to 115 Kelvin. So crystalline solid is being heated from 0 Kelvin to 115 Kelvin. So by heating, the randomness increases. So here in delta S will be greater than 0. Then this is the reaction where we are converting 1 mole of solid into 1 mole of solid and 2 mole of gas. So from we are going from solid to gas. Like there are increased mole of gas. So this is done entropically. Disorder is increasing here as it is converted into gas. So this is an entropy increase process. Again, then H2 gas to 2H gas. Again, from 1 mole it is converting into 2 mole. So again it is delta S will be greater than 0. So entropy is increasing as the number of mole of gases are increasing, in randomness is increasing, and hence entropy is increasing. So for option 1, entropy is decreasing. For option 2, entropy is increasing. For option 3, it is increasing, and option 4, it is increasing. So answer is 2, 3 and 4. 2, 3 and 4. Answer B is the correct one. It is solved here. Liquid entropy is more than the solid, so that is delta is negative. As temperature increases, randomness increases, delta is positive. More gaseous species is in product, delta is positive. More gaseous product in again, so delta is positive. Calculate the number of heat necessary to raise the temperature of 60 gram of aluminium from 35 degrees Celsius to 55 degrees Celsius. Molar heat capacity of aluminium is given. So calculate number of moles, I guess. Yeah. So we need to calculate. Okay. Delta H. We need to calculate delta H in kilojoule. So this is typing mistake. So we need to calculate in enthalpy only, and we are given molar heat capacity. So, and this temperature, this is the mass of the compound aluminium. So we know molar mass, we know mass. So N is equal to number of moles is equal to mass upon molar mass. From there we can calculate number of moles, and we know that delta H is equals to NCP delta T, and delta T it is given that 35 degree, it is changing from 35 degrees Celsius to 55 degrees Celsius, so it is 20 degrees Celsius or Kelvin, it is same. So change in temperature is 20, delta T is equals to 20. NCP, and we know number of moles, mass upon molar mass. Mass is 60 gram, molar mass is 27 gram per mole. So 60 upon 27, Cp is 24 joule per mole per Kelvin, and then delta T is 20. So by solving this, we are getting this delta H value. So this is the typing mistake here. So this is calculate the enthalpy. Or you may say that calculate the heat of the reaction, you can say. Correct value of Q, delta U and W, heat, internal energy and work done in free expansion is. So we know, we have solved one question also, and I have shown in my slide also that for a free expansion there is no work done, there is no change in internal energy, there is no exchange of heat, and we know that there is no change in temperature. So answer is all are 0. So B option is correct for this. So for vacuum, P external is 0, work done is 0, delta U is equal to Q plus W, so Q is equal to minus W, so Q is equal to 0, so answer is B. So let me okay, answer is B. Since we know that the temperature is not changing, so it is isothermal process only. So next question. A sample of 2 mole of an ideal gas O2 at 500 Kelvin is expanded from 5 liter to 50 liter under adiabatic and reversible conditions. So this is the key, adiabatic and reversible condition. The change in internal energy is close to, we need to calculate change in internal energy, that is delta U. Okay. Sorry. So okay. Example of expanding from 5 liters under adiabatic and reversible area. Change in internal energy is close to. Okay. So N is equal to 2 mole. Sorry. Sample N1 is equal to 2 mole, and temperature is 500 Kelvin. Volume is 5 liter. V1 is 5 liter, and V2 is 50 liter. So we know that this equation we have used earlier as well. T V to the power gamma minus 1 is equals to constant. So again we are solving the same equation, T2 by V1, that is that we expand it and solve it there also. So T2 by T1 is equal to V1 by V2 gamma minus to the power gamma minus 1, and since gamma is given, yeah, CV is given, Okay, R is given. So CV is given, R is given, CP we can calculate here. CP minus CV is equal to R. Sorry, CP minus CV is equal to minus NR. CP minus CV is equal to NR. So by using that formula, we can calculate CP and CV both, and then from CP by CV we can calculate gamma. So that gamma we can put it here. So for this question, CP is equal to 7 by 2k, CV is equal to 5 by 2k. So then CP by CV is equal to 1.4, that is equal to 7 by 5. So again T2 and T1, T2 is given, T2 is we can calculate from here. T1 is given, V1 and V2 is given. So from here we can calculate T2. So we know T1, we know T2. So now we can calculate delta T. We know we have temperature T1, so and we have calculated temperature T2, so we can calculate delta T. And CV is given, number of moles is given. So we can calculate this delta U, that is equal to that is equal to CV delta T. So N is 2, CV we have calculated here, this 5 by 2 R is 8.314, dt is equals to this minus 300.35. By solving this, we are getting minus 12.5 kilojoule. Minus 12.5 kilojoule. So this is from my side. Thank you. If you have any doubt in these questions, or if you want to know anything from these slides, you can ask. Thank you. So I am leaving this meeting now. You can mail me there, or you can ask some question in this discussion forum also. We will solve there. Okay. Thank you so much.